Hello, grade 11s. Today we're going to start talking about standard deviation. Now, the other day we started off by doing an activity called Finding Desmo, where we were simply looking at putting fish of different masses into a fish tank and seeing how that variety of fish that we added changed the standard deviation. Now, we really didn't ever give it a formal definition, but kind of played around to see how adding values of different sizes affected that standard deviation overall. So let's give it a formal definition. Standard deviation is a measure of how spread out or dispersed the values in a data set are from the mean. Okay, so standard deviation is a measure of how spread out or dispersed the values in a data set are from the mean. Now, when we take a look at what we can do so far, we know how to calculate that mean. We can do it by hand. We can do it in our calculators. We have those skills. Now, when we take a look at each of the data values, if those data values are really, really close to what that mean is, that means the standard deviation is going to be small. So if the standard deviation is small, it means most of the data points are close to the mean. If the standard deviation is large, it means that the data points are more spread out from the mean. So a larger standard deviation means that my data values are more spread out or further away from that average value. Now, over here, we talked about our Finding Desmo activity yesterday, where we put fish into fish tanks and the fish had different masses. And as we did this, we had this chart or graph show up on the right. Now, this is called a dot plot because there's a dot for every single value that exists. Now, at the bottom, there was a line, and that line represented the average. Now, in most of our examples, that line looked dotted, but that vertical line represented what the average was of those fish masses. So here we have 7 green fish, all weighing 5 grams. So on my dot plot, I have that being represented here. Now, of course, the average of 5, 5, 5, 5, 5, 5, and 5 is going to be 5. Right? You add up all of those values, divide by the total number of data values, and you get your average, which will be 5, which is why we have a standard deviation of 0, because we have absolutely no spread or dispersion from my data values in comparison to the mean. They are exactly the same. When we talked about adding fish that were different from each other, we ended up getting a mean that would be somewhere in the middle of their masses. And of course, depending on how many fish of different masses we added, the average would change. But again, that average would be calculated just as we would have before, either by hand or with our calculator. Now, this average for this fish tank that I have is around 4.6, 4.7. I'm just estimating here. I don't know exactly. I didn't do the calculation. But my data values are all pretty close to it, right? The data values I have are either 4 or 5, which is really close to the number 4.7, which is why we have this relatively small standard deviation. Now, if I had a fish tank like this next one, I could still calculate the average, and the average, if I'm taking a look at it, is probably just about 5, just over 5 grams for the average mass of the fish in the tank. But a lot of my data values are not close to that average. This one is. This one's reasonably close, a little further off, but we've got quite a bit further away. Because my data values are more spread out from where my average, my mean is located, then I'm going to have a larger standard deviation. Now, the largest possible standard deviation we were able to find is when we took our absolute highest value we can possibly find, which is a fish of 10 grams, and the absolute lowest data value we can possibly find was our fish that was 1 gram, and we put an even amount of both of them in the tank. And the reason we wanted an equal amount of both of them was so that our mean, our average, would be right smack dab in the middle. If I added another fish here, then my average would go up a little bit, okay? So the fact that there's an equal amount means that the average is right smack dab in the middle, which means my data values are really, really spread out from what the average value is, giving me a large standard deviation. So yesterday we went through and talked about how we can conceptualize standard deviation before we understood the math behind it. Now, when we take a look at standard deviation, when we were going ahead and going through our previous notes in 5.1, we talked about how to use our calculators to find the mean, the median, the max data value, the min data value, and all of these other different things. And we introduced this notation. This notation is a lowercase sigma. It is a Greek letter, and it's used to represent standard deviation. So it kind of looks like a lowercase o with a line coming out the top, but that's the symbol we use for standard deviation. Now, as we were going through the list of things our calculator was able to provide for us, there was technically 2 things that represented standard deviations. They were just 2 different types of standard deviation. And although in this class we are only going to be focusing on the population standard deviation, and that's the only one we're ever going to use, it's worth noting that there are different types of standard deviation, so I do want to briefly talk to you about what that is, in case you ever come up with a statistics class again. So let's say, for example, I wanted to find the average height of a student at St. Mary's who's in grade 11. Well, I have some options. I can go and measure the height of every single grade 11 student here in this building and then figure out the true average height. And why I'm saying true average height is because I literally collected every single possible data value I could when I was collecting this data. We collected data from the population. Now, that population standard deviation is going to be fairly accurate because I am getting that standard deviation from every single data value I was able to collect. I collected it. Now, the other thing I can do is I can say, you know what, that's a lot of students to collect the height of. I could instead take a sample, which is a smaller subset of the larger population. Now, a sample isn't always as accurate because I am making some assumptions that are associated with it. I'm assuming that whatever results I get from that sample are true for the whole entire population, which could be true, but it's also my best guess here. So a sample is not necessarily as accurate as collecting data from the whole entire population, which means the standard deviation, the measure of spread from the true average, is going to be a little bit larger, which makes sense. We are less certain about the average. We are less certain about all of the data values and where they lie, which means we're going to have a larger spread or larger amount of dispersion within our data values. So that's why there are 2 of these values here. We will not be using the second one, but I did want to just mention what it was. All right, so we are going to go ahead and start with some calculations. Now, before I go ahead and do the calculations with you, I want you to pause the video and try calculating the mean, median, mode, and standard deviation for each of the data sets below. Did you do it? I hope so, because I'm about to. Now, these data sets don't have units associated with them, so my answers for mean, median, mode, and standard deviation will not have any units either. But something that you might have noticed is that the mean, median, and mode for the first data set was all 10. Nice. And then the standard deviation is 2.55. For a data set we actually got the exact same mean, median, and mode, except this standard deviation was only 0.5, which I probably could have predicted, not necessarily the exact number, but I could have predicted that this is going to have a smaller standard deviation, data set 2, than data set 1, just by looking at the values in the data set. In data set 2, most of my values are 10. I have 1, 9, and 1, 11, but most of them are 10. They're really, really close to what that average is going to be. Whereas in data set 1, I've got a lot of variation. I've got some small numbers like 6, and I've got some bigger numbers like 14. So my data values are much more spread out, which means I can anticipate that my standard deviation will be higher for data set 1 without having to calculate it. But if I wanted to know the exact value, that calculation would be necessary. Okay, standard deviation, as we know, is a measure of the dispersion or variability of a set of data values from its average, which means it's actually really useful when making decisions across a variety of different domains, such as insurance companies using that data value, or warranties being decided as to how long we should set them so that we, the company, can provide some quality, service to our customers without actually having to repair everything that goes wrong. We want to make sure our warranty is set so that, yeah, fine, we'll fix something if it's our fault. If it's a one-off, no problem. But I don't want to fix the majority of the devices or the couches or whatever it is that I'm selling. So let's talk about insurance. Insurance companies rely on standard deviation to assess risk and set premiums. For instance, MPI uses historical accident data and its standard deviation to determine the likelihood and severity of future accidents for various regions. So let's imagine that MPI was collecting some data, and that data they collected was from 1,000 drivers. And what they did was they tried to figure out how frequently people got into accidents. So in this case, what would a higher standard deviation mean to the insurance company in the context in this scenario? So MPI looking to assess likelihood and severity of accidents. What would a high standard deviation mean? Well, a high standard deviation in accident frequency leads to greater uncertainty, right? There's more spread, there's more unknown. The values are further away from the average, which means we can't predict the exact number. It could be really high, it could be really low, it could be really close to the average. We don't know, which involves a greater risk to the insurance company. Because if you as a company can't predict how much you're going to have to spend to help make the repairs of accidents that take place, or make the insurance claims and cover the costs for those insurance claims, that's a really big risk to the insurance company. So the higher standard deviation in accident frequency the greater the uncertainty of how often accidents will take place in the future, which leads to greater risk to the insurance company. Now, when we take a look at that, we want to talk about how might that standard deviation affect their decision-making regarding premiums. So we're talking about MPI. They are in charge of covering the costs of all of those accidents. How do they cover the cost? Well, they charge us money every single year so that they put in one giant pool, and then every single accident that happens, they pull from that pool of money to pay it off. Now, if they can't figure out how many accidents are going to take place, it's going to be really hard to figure out how much they should charge us, right? Whereas if we had a low standard deviation, I would know, okay, well, the likelihood of accidents taking place, or the quantity of accidents taking place, is close to the average. I can probably charge you enough money to pay off that average amount, maybe with some buffer, some room for extra. But then that way, I'm not under in the amount of money that I've charged. Whereas if I have a higher standard deviation, there's a higher level of uncertainty. There's more risk in the company because I don't know what the actual value of, or the actual quantity of accidents that are going to take place in the future year is going to be, which means I'll likely charge you more so that I could cover my butt if there's a really high number of accidents. So let's write that down. The higher the standard deviation, the higher the level of uncertainty, and risk for the company, which leads to higher premiums. And of course, vice versa, right? The lower the standard deviation, the lower the level of uncertainty, which means the less risk for the company, which could lead to a lower premium. Okay, we have one example left. And in this next example, we are imagining that you work for Apple. And the company is testing out two prototypes for the latest iPhone. There's the iPhone Alpha and the iPhone Omega. In the testing phase, Apple has half of its employees test out each phone and report the time in which they experienced device failure. The data for each device is shown below. Now I can see this data does have units. The units are in years, so when I calculate the standard deviation, when I calculate anything, I need to make sure that my years are the units for those calculations. Now, for part A, I want to determine the mean and standard deviation for each device. So I'm going to find for Alpha what the mean is and what the standard deviation is. And I'm going to do the same thing for the Omega. Now I want you to pause the video, of course, and I want you to go ahead and calculate that to 2 decimal places, the mean and standard deviation for both devices. Go. And welcome back. So the mean for the iPhone Alpha was 5.17 years, whereas the standard deviation is 0.16 years. For the Omega, we got 5.37 years as our average time before device failure, and our standard deviation of 0.65 years. Now, we want to talk about two things. What does a low standard deviation mean in the context of this scenario? And what does a high standard deviation mean in context to this scenario? I want you to think about it. And let's talk. So, when I take a look at low standard deviation in general, low standard deviation means that my data values are really, really close to the average. So in context, if we're talking about the number of years until the devices die, a low standard deviation means that most of these devices are performing similar to the average lifespan. So most of the devices are performing similar to the average. Average. Okay, When we talked about higher standard deviation in general, a high standard deviation means that a lot of my data values might be more dispersed or widely spread. In this context, that means that my devices, or at least some of my devices, are not performing similarly to the average. They are more widely dispersed, making it hard to predict how long the next device of that type is going to last. So let's write that down. So more of the devices are not performing similarly to the average. Making it hard to predict how long a phone of that model, so the whatever phone we're talking about, so phone alpha, phone omega, etc., how long a phone of that model will actually last. Right? Because that standard deviation, the higher it is, I don't know if that value is going to be really close to the mean. It could be in theory, but it could also be really heckin' far, and that could be on the high side, which is great for how long a device lasts, but it could also be on the really low side. Now, why is this useful? Well, what if I'm part of that company and I want to help the company make a decision about how long the warranties should be good for? Well, let's think about it. If I am a company and I'm offering a warranty, I'm doing it for two reasons. Well, one reason, I guess. And that reason is to make the customer feel good, such that if my product didn't work as it was expected, then they would rest assured knowing that I would do something about it. Maybe I would replace it, maybe I would fix it, etc. Now, I'm doing that for good customer service. But companies are really out there to make money. Like, obviously, they want to have good customer service so that customers come back and keep on purchasing from them. But they don't want to offer a warranty for like 20 years on a phone because the phones aren't going to last that long. And if they had a warranty of 20 years, well, then instead of people purchasing a new phone, they would keep on claiming the warranty, which means I would end up having to replace all of these phones or fix all of these phones, and that would be a really costly thing for my company to do. So companies need to find a balance as to how long I should set a warranty to both make the customer feel good, but also not too long such that I don't have to actually do a lot of work into fixing devices. So I want to set the warranty before the typical device starts to die. Okay? So when I take a look at standard deviation, a standard deviation really tells me the reliability or how close to the average my data value is. So if I'm looking up at the iPhone Alpha and I'm saying, okay, it lasts 5.17 years with a standard deviation of 0.16, okay, I can comfortably set a warranty for a year, even 2, maybe even 3. Honestly, 4 might also seem realistic. 5 might be pushing it, but 4 years, why not? Especially when I look at these data values, none of these lifespans, none of these lifespans are really in the 4s anyways. So if I set my warranty to be 4 years, like, this is the closest I'm getting. So if there's one that maybe in the batch didn't work out, fine, I could replace it. Not a big expense. But if I have a higher standard deviation, I've got a bigger spread. Yeah, I can set it to 1 year, 2 years, 3 years. 4 years, I'm coming a little bit close. I'm a little bit skeptical because there's way more data values that are in the 4s now. And I, as a company, don't want to replace 33% of these devices, right? 5 out of 15. That's a lot of money. So I would probably set my warranty to be a little bit lower. So let's kind of write a decision kind of down in words together. So when the standard deviation is low, companies can more reliably predict how long the next device will last. How long the next device will last before needing repairs. As a result of the lower uncertainty, they can more confidently offer warranties with specific terms and durations. Okay, so when the standard deviation is low, companies can more reliably predict how long the next device will last before needing repairs. As a result of this lower standard deviation, or this lower uncertainty, they can more confidently offer warranties with specific terms and durations. Okay, so today we talked about standard deviation. We talked about what it officially means, how to calculate it, but also how standard deviation can be used to make decisions. All right, that's it. That's all. Please continue and work through the practice that follows, but otherwise, have a great day. Bye.